Continuing our discussion on transformations, we've already discussed horizontal and vertical shifts. Now we're going to move on to vertical compressions and stretches. Let's first look at the core function of x squared. X squared has the following points, and when I connect the points, you can see it has a parabola effect. So now what we're going to do is we're going to multiply that squared function by a number in front. And we're going to see what's going to happen to the graph. So let's use just a table of values to determine what's going to happen. So I'm going to use the numbers 0 and 1, 2, let's do -1 and -2. So when I plug a 0 in for x, I actually get 0. When I plug a 1 in for x, I get 2. When I plug a 2 in for x, 2 squared is 4 times 2 makes 8. If I plug in a -1 for x, that becomes +1 times 2 is 2. And a -2 becomes 4 times 2 is 8. So when I plot these points, here's the new graph of my parabola. Okay. So in essence, it is the same vertex, the same bottom point, which is 0, 0, but it looks like the graph is taller. Some people say it's skinnier, and both of those are true. But what in essence is actually happening is it's actually becoming stretched. So think of the vertex as being a locked point. Anything on the x-axis is locked in position. Then we take all of these points over here and we literally stretch them and pull them upwards. So we're going to take this point at 1, 1 and we're going to stretch it up. So now it's going to be located here. We're going to take this point, we're going to stretch it up. So now it's located here. We'll take this point and we'll stretch it up. So now it's located here. And this point's going to be stretched. So it's located here. So in other words, every point got vertically stretched by a factor of 2. So this point is now twice its height. It used to be only 1 tall, now it's going to be 2 tall. This point here was 4 tall, now it's going to be 8 tall. So every point, every y, got multiplied by 2. So this was a vertical stretch by 2 times. So let's look at what's going to happen if I put like a number smaller than 1 in front of the x squared, like 1/2. So let's use the same values over here, and let's see what happens. If I plug in a 0 for x, I get 0. If I plug in a 1 for x, I get 1/2. If I plug in a 2 for x, 2 squared is 4, half of that is 2. -1 is going to give me the same value as +1. -2 is going to give me the same value as +2. So when I plot these points, 1, 1/2, 2, 2, okay, it's still a parabola. The vertex is still locked in place. The vertex has not moved from the origin. It is at the origin for all of them. That is an anchor point. It is locked on the x-axis. What does happen is each of these individual points will be vertically compressed down to half of its size. Since it's a number smaller than 1, this number is going to be a vertical compression or squeezing of 1/2. So this point that used to be here at 1 is now going to get compressed down to half of its size. So this point here got now compressed to half of its size. This point up here is now going to get compressed to half of its size. So it moved down here. So in other words, every point that used to be up here is now going to get compressed down to half of its size. And when you flatten out a graph, it makes it appear wider because you're flattening it out. Same thing with a stretch. If I take all of these points and I pull them upward, you're giving the illusion that it's a skinnier graph, but you're really just stretching it up. So the conclusions that we're going to make here at the bottom of these graphs are that when f of x is multiplied by a positive number, you get the graph of a times that function. So the new graph, if a is greater than 1, like in this scenario here where a was 2, so if a is bigger than 1, you're actually going to vertically stretch the graph. But it'll be vertically compressed if the graph of a is between 0 and 1. In other words, if it is a number less than 1, like a fraction, then it will be a compression. So this says the graph will be 2 times its height. This graph says the graph will be 1/2 times its original height. So we're going to use this information about vertical shifts to do some more examples on the next page. Okay, so let's look at this graph here. We have the graph function of the square root function. The square root function, if you recall, has the graph of a sideways parabola, but it does not have any other half to the graph. So we're going to take that square root function, we're going to multiply it by 2. Remember, the origin, the vertex, wherever it crosses your x-axis, is an anchor point. It does not move unless you vertically shifted it by adding or subtracting a number. So that is an anchor point. Now every point that we have graphed over here is going to get either vertically stretched or compressed. Since there is a 2 in front, this will be a vertical stretch times 2. So this point is going to be now, instead of 1 tall, it's going to be 2 tall. This point here, instead of being 2 tall, it's going to be 4 tall. So it's going to be twice its height. So this is what the graph will look like. You can see every point has been stretched and pulled upward to create this graph over here. Now we're going to do this one again, but this time we're going to multiply it by 1/2 in front. Now remember, the vertex never moves. It is the anchor. And then each point will move from there. 1/2, since it is less than 1, will be a compression. So we're going to take each of these points and we're going to compress them down to half its size. So this point is now at 1/2 and this point is now at 1. So you can see it is a very short graph because all of these points have been compressed down, creating a much flatter graph. Also, I could show you what these would look like using transformations down below. So in my graphing calculator, I put in the 3 functions above, and we're going to see what they look like from left to right. So here's the first function, which is the square root function. Then when we stretched it by a factor of 2, so you can see the second graph up here is twice as tall as the original, then the bottom graph is a vertical compression, meaning it's been flattened out to half of its size. Okay, so the third part to this section is graphing reflections. So we're going to talk now about using reflections over the x and the y axis. So let's first start with the square root function, which we just got done discussing above. We have these key points. And now I'm going to put this negative in front of the function. Let's see what it does to my graph by plotting some points. So here I've got points at 0, 1, and 4. So let's put those in and see what happens. So my point, which was at 0, 0, well, that's still at 0, 0. When I put a 1 underneath here for x, I get square root of 1, which is 1, but then the negative in front tells me I get a negative 1 for y. If I put in a 4 for x, that gives me negative square root of 4, so that's a negative 2 for y. So my points, my 3 points that I had over here on the left, are now going to be located at the origin, 1, negative 1, and 4, negative 2. So what happened to my graph? You can see that my graph that used to be up here in the first quadrant is now down here in the fourth quadrant. So this was an x-axis reflection. It flipped over the x-axis and is now down here in the fourth quadrant. What happens if I put the negative on the inside of the function? On the inside of the function. Okay? Remember, any transformation that happens outside of the function will always be a vertical transformation. So this graph was a reflection vertically. A negative on the inside will be a horizontal transformation. So its reflection will happen horizontally. So it's probably going to be a y-axis reflection. We're going to prove it by finding points. So let me plot these same points over here. I put in a 0, 1, and a 4. Let's see what happens. Well, negative 0 is 0, so I get the origin, so that point was locked in place. But if I put in a 1 here for x, I cannot take the square root of a negative 1. These are going to be undefined because it turns a negative on the underneath the radical symbol. So now maybe I can actually put some negative values in. If I put a negative 1 in for x, negative of negative 1 is positive 1, so I can actually put a negative underneath because it has the extra negative sign. Negative 4 for x gives me positive 4, square root is 2. So when I plot these 2 points, it is indeed a y-axis reflection. If I took this original graph and I reflected it over the y-axis, you can see that this graph would now be over here in the second quadrant, which is exactly what we've done. So again, a negative on the outside of the function is an x-axis reflection, but a negative on the inside of the function is a y-axis reflection. So let's reiterate. Negative on the outside of the function is going to be an x-axis reflection. A negative on the inside of the function is a y-axis reflection. So let's do a couple more of those here. Let's see if we can get some more practice. So we've got the x squared function here, which is the parabola. I always like to plot the key points because it's easier to move them once you have some key points plotted. Remember, a negative on the outside of the function. This is on the outside of the function. If it was on the inside of the function, it would look like that. So this negative is on the outside of the function. When it's on the outside of the function, that means it's going to be an x-axis reflection. So we're going to take all of these points and we're going to reflect them over the x-axis. So origin's not going to move. This point's going to get reflected over the x-axis. This point will get reflected over the x-axis. This point, which is 4 high, will be reflected over the x-axis, and so on. So now it becomes an upside down parabola. What happens if I do a y-axis reflection? Let's say I actually do this graph, which is a y-axis reflection. So that means I take the original graph and I flip it over the y-axis. What would the graph look like? It would be the exact same graph, because when I square a negative, you actually get the original back. So that's why we didn't really do an example of that, because you're going to end up with the exact same graph back by doing a reflection over the y-axis. Let's try another one. This time we'll graph the cubed root. The cubed root function looks like this. So we're going to take those 3 points and we're going to reflect it. This time the negative's on the inside of the function, so that's going to be a y-axis reflection. So we're going to take each of these 3 points and we're going to flop it over the y-axis. So the origin doesn't change, but this point will be reflected over the y-axis. This point will be reflected over the y-axis. So now my new graph will look like this. Here we're asked to graph x squared and then we're asked to also do these reflections in addition to that. So there's a couple of things we need to do. The first thing it wants us to do is do the reflection first. There's actually 2 transformations that are occurring here. There is a vertical stretch times 2, and then there's also a negative on the outside of the function. A negative on the outside of the function is an x-axis reflection. So we're going to take this original graph and at the same time we're going to take each point and stretch it and reflect it. But remember that anchor point does not move until I shift, which will be in the last part over here. So let's take this point 1, 1. Let's first do the x-axis reflection. So that means this point now is down here, but then we're going to stretch it by 2. This point at negative 1, 1 is going to do an x-axis reflection, and then we're going to stretch it by 2. This point at 2, 4, which is right here, is going to reflect over the x-axis, but then it is going to stretch by 2. This point over here at negative 2, 4 is going to reflect over the x-axis, and then it's going to stretch by 2. So I've already done the vertical stretch. I've already done the reflection. Now I need to do the shifts that are over here. These shifts are going to take this graph and then I'm going to shift it. The add 5 is a vertical shift up 5 units. The negative 3 is going to be a horizontal shift. Since it's negative, that means it's going to go right 3 units. All right, so now we're going to take this graph because we already have The reflection and the stretch already taken place. So now we're going to take that graph here and we're going to vertically shift every point up 5 and right 3. So let's take the origin and let's move it up 5 and right 3. So now this is going to be the top of my parabola. This point at 1, -2 will also go up 5, right 3. This point will also go up 5, right 3. It's pretty interesting how that all comes together. Let's see how we did using technology. Got the 3 graphs here. Here's the first one, which is x squared. Then we do the reflection and the stretch. Then we take that graph and we shift it to the right 3 units. And it doesn't look like I moved it up 5. Nope, I did not. Let's try that again. Here's the original. Here's the reflection and the stretch. Then we move it right and up, and there it is. And this last graph should match exactly what we have over here. Finally, we have one last problem to tie it all together. So on this last example, we're going to take the square root function, which we have some key parts for, and we're going to do these transformations to it. Negative on the outside of a function is an x-axis reflection. Always do what's on the outside first, just like using PEMDAS, meaning do your multiplications first before you do any additions and subtractions. If you shift first and then do your reflections, you will get a wrong graph. So let's first do the x-axis reflection. So we're going to take this graph, we're going to flip it over the x-axis, so it'll be down here in quadrant 4. Then, now that that's already been done, now we're going to add 4 on the inside of the function, which means we're going to move it left 4 units. Then we're going to add 3 on the outside of the function, which means we're going to move it up 3. So all of these 3 points are going to move left 4 and up 3. So my origin will move left 4, up 3. This point will move left 4, up 3. And this point over here will move left 4, up 3. So this is what the end result would look like. Now, of course, you can always check that with technology. And at the bottom of this set of lecture notes, I also have provided you with a summary of everything we discussed. So this is kind of going to be a good guide for you when you're doing your homework. So I zoomed out a little bit so you could see them all. So all of the techniques that we talked about in this class is located at the bottom of these lecture notes, which you can print from the class. And you can see all of the transformations we discussed, from the vertical shifts on the outside of the function to the horizontal shifts on the inside of the functions, to the stretches and compressions. If the A is on the outside, if it's bigger than 1, it's a vertical stretch. If it's less than 1, then it's a vertical compression. There is also such thing as a horizontal stretch and compression, which we didn't do an example of, but that's when you multiply A on the inside of a function instead of on the outside of the function. And then lastly are the 2 reflections that we also discussed. So this is a good review of all of the transformations that also took place in this section.